Lagrangian mechanics, it came about, 1780s, right? And in Lagrangian mechanics, again, we are trying to look at a system, and in this system, we are trying to again predict what it will be the equation of motion of objects. And when we apply the Lagrangian formulation, it is sometimes useful for us because when we look at complicated problems, the equations that the Lagrangian has suggested is easier to work with. Okay, and at a basic idea, what Lagrangian of a system is given by this capital L, and it is just the sum of kinetic energy of the system minus the potential energy of the system. Okay, and generally in textbooks it is written as T minus V. Okay, T stands for kinetic energy and V stands for potential energy. And what we do is we look at this Lagrangian for any system that we want to study. Okay, and then we apply the equation of motion. Okay, and the equation of motion basically is something like this, that the time change of the partial derivative of this Lagrangian with the first derivative, okay, with respect to x, okay, those are generalized coordinates, okay, minus the partial derivative with respect to x, okay, so these are two different things, okay, will be equal to 0. Okay, so this is the equation of motion that we will be using. Okay, and for any system we have to first find what is the value of L, which is the sum of kinetic minus potential energy. Okay, so if you can do that for any system, you can then calculate the partial derivative with respect to x dot and partial derivative with respect to x, and then we can plug that into this equation, and from here we can get the result of equation of motion. Okay, so that is the basic idea. All right, now what is this x dot? X dot, which some of you might be familiar, is just your velocity. Okay, and x just represents the position. Okay, and so let's take an example so that what we are writing here makes more sense. Object, let's say this is the ground level. Okay, and we can define this as position y is equal to 0. Okay, and you have an object that is going to fall from certain height here. Okay, and let this position be y0. Okay, now we are just letting go of this object from this position. Okay, so initially this object will just have your potential energy, right? And the potential energy will be given by some value of mgh, right? So you get mg, and whatever is the value here, let's say this height is some value y, then the potential energy is y. Okay, so the Lagrangian, which is given by your kinetic energy minus potential energy, okay, for the first case the Lagrangian will be just minus mgy for this case, because there is no kinetic energy, the object is here, you're just letting it go, so it is going to drop. So once the object starts dropping, we know that the potential energy will be converted into kinetic energy. So at this bottom position here, it has completely converted all its potential energy into kinetic energy. So the value for Lagrangian here will be 1/2 times your mass times your velocity square. Okay, so again, velocity we can write it as 1/2 mx dot square. Okay, so for this complete system, if you're trying to write what the Lagrangian is, you can write it as 1/2 mx dot square minus mgy, and this is your complete Lagrangian for this system. Okay, very simple. A ball free fall. Okay, so this is a situation of free fall of an object. Okay, just because of gravitational force. Okay, so now let's apply our equation. We know we want to calculate this term, which is equation of motion, which is d by dt. We want to take the partial derivative with respect to x dot of this L. Okay, and then we want to take partial derivative with respect to x of this L. Okay, and we know this is your total Lagrangian. So first thing, let's calculate d by dx, partial derivative with respect to L. Okay, so that means other terms are, if you take derivative with respect to x dot, other terms are constant, so that term will become 0. So if I just take the partial derivative with respect to x, then here, we can change the coordinate here from this situation to a generalized coordinate. So instead of y, we can just write x. Okay, so it is again a generalized coordinate, so it applies to this situation. Okay, so we can say just let y become x. Okay, so now we are only dealing with one-dimensional motion. Okay, that's what this means. So don't get confused. Okay, now I'll just write it down. So we are using generalized coordinates. Okay, when it goes three-dimensional, it will become r and so on. So these are just normal coordinates of the system. Okay, so if I take partial derivative with respect to L, then I have to just take partial derivative of the second term. This is a term with velocity in it, so we cannot take derivative of this because it's a partial derivative. So I will just get minus mg. Okay, so that is my term here. Now the first term will be partial derivative with respect to L with respect to x dot. Okay, so then I have to take the derivative of this first term. Okay, not the second one. Second one is 0. So I get 1/2 m, and derivative of x dot square will be 2 times x dot. So I get 2 and 2 will cancel. I just get mx dot. Okay. Here, let me see. Dx. All right, I think I'm all good. Good. So now I want to take d by dt of this function. Remember, d by dt is of this function right here. Okay, so let's not get confused. All right, only the first term. So if I take d by dt of mx dot, which is dx by dt, I just get mx double dot. Right. Remember, x double dot is d square x by dt square. Okay, and did we define x dot? X dot was dx by dt, right? That is your velocity. So my first term becomes mx dot. Okay, so that is my equation number 2. I can write that down. Okay, so from equation 2, I get this first term is mx double dot. Okay, and the second term is minus of minus mg. Okay, is equal to 0. Okay, that is what I should be writing here. This equation has to be equal to 0. Okay, so from here you can see I get mx dot plus mg is equal to 0, and now m and m is common, so I get x double dot is equal to minus of g. Okay, so what does this equation tell me now? It is telling me that in this system I have some acceleration. D square x by dt square is acceleration, and that acceleration is minus of g. Okay, so that is what it is telling us. Okay, so from here what you can do is, if I look at this equation again and I just say, okay, I have x double dot is plus g is equal to 0. That means I have essentially this is dv by dt plus g is equal to 0. And now I can do my integration. I can just write this as dv is equal to g times dt, and then I can integrate this on the left hand side and the right hand side. So I get integral of dv is integral of g dt, right? Something like this. There is a minus sign. Okay, so that is just for sign convention because of the problem. Okay, so I have a minus sign here. So now I can get v is equal to minus gt plus some constant term. Okay, and similarly I can do it again. I can write dx by dt is equal to minus gt by plus c, and then again I can do this. I can do integral of dx is minus gt dt plus c dt, and then I can integrate this, and I get x is equal to this will become minus gt square by 2, and then this will become ct, and then I will get another constant. Okay, so I get my equation of kinematic equation. Okay, x is equal to x0 plus some constant times t plus some acceleration times t square 1/2 at square, and that is my equation. So my complete system I have solved by just starting from the Lagrangian by saying that I need to know only the kinetic energy and potential energy of the system. If I know that, then I can figure out what is going on in my system. I can figure out the acceleration of this system, and from there I can again work out and try to solve, and now I'll get my kinematics equation, right? Okay, and this is what is determining how the system is behaving. Okay, so that is one way to look at problems, as to if you know what the kinetic energy and potential energy of the system is, and you have defined your system, then you can actually go ahead and find all the remaining parameters of your equation. Let's do another quick example so it will make more sense. Okay, now remember we had done the case of spring many times. Okay, we had taken that, let's take a spring. Okay, and there is a mass attached to the spring. Okay, and this spring is moving with some, this mass m is moving with some velocity. Let's define that k is the spring constant, and then what did we find out in this case? What is the equation of the spring? Remember, x double dot plus k by m x is equal to 0. I mentioned, and what is this k over m? This is related to omega square, and omega is the frequency of the oscillation, and this represents the motion of your spring, which is a simple harmonic oscillator. So this is known as a simple harmonic oscillator equation. Okay, x is the position of this spring. Okay, this is the solution. X is equal to a cos omega t. Now, according to the Lagrangian, we have to know what is the value of L. Okay, that means kinetic energy minus potential energy. Okay, and we know that the kinetic energy of whatever mass is moving is 1/2 m v. V is x dot square. 1/2 mv square is the kinetic energy, and we also know what is the potential energy of the spring. Like somebody's mentioned, potential energy of the spring is 1/2 k times x square. Okay, so that is our Lagrangian. We are familiar with this Lagrangian. All we have to do is now we have to calculate this equation: d by dt partial derivative with respect to x dot of this L term minus partial derivative with respect to x of this Lagrangian. Okay, so let's calculate the partial derivative with respect to x of this L. Okay, so that means we don't care about this first term, it's partial derivative. Only
Sir,
the second we have to worry about. Yeah.
Sir, x dot you said is dx by dt, right?
Yes.
So what does it mean when we said dl by dx dot?
We are differentiating L with respect to velocity. So we are taking
Achha,
partial derivative here. It means that
yeah.
we are only changing this variable and other variables are constant.
Yes, sir. Understood.
So we are saying the velocity is changing, but the position is not.
Yes.
And that is certainly a possibility. Okay. So whenever we take partial derivatives, we are saying that we are only changing this variable. All the other variables in the system are constant. And this is a very common strategy, when we are trying to define motion. So for example, in a three-dimensional room, okay, I want to enter from the door here, and I want to go in some position, let's say somewhere in the ceiling in between here. Okay, so instead of directly going like this, what I can do is I can go something along the x value, then I can go somewhere along the y value, and then I can go somewhere along the z value. And that is essentially what we are doing. When we are doing partial derivatives, when we move along x, we are keeping y and z constant. Then we move along y, we keep x and z constant, and then we move along z. So those derivatives are actually the motions, right? We are trying to see how things are moving or changing. So when we change one variable and use partial derivatives, we are saying that let's all the other variables be constant, and so only this variable will change. So when we move along the x direction, all the other values we will ignore, that they are not changing. Okay. Make sense?
Yes, sir.
Yes, sir.
Okay, good. So first we will take partial derivative with respect to x. So all these other variables, they are constant. So we cannot take a derivative of this. It will be 0. So we get again minus half, and you have kx square. So k is constant, and then derivative of 2x is x square is 2x. Okay. So you have 2 and 2 will cancel. So you get minus kx as your partial derivative with respect to x of this Lagrangian. Okay, so that is your second term. So again, now we can calculate the first term, which will be with respect to x dot. Okay, so that would mean we have to take partial derivative of this term here. So again, you get 1/2 m and 2 times x dot. Okay, which is the derivative of this x dot square. So again, 2 and 2 will cancel. So you get mx dot. However, there is a d by dt in front of this. So when I take d by dt of this partial derivative with respect to x of L, basically I get m, and then I have to take another derivative of this. So I get mx double dot. Okay. So now look at this equation. Again, when I plug this equation and put all these values here, okay, in this equation 2, so I get first term is mx double dot and get minus, and I have a minus kx. So I get plus kx is equal to 0. Or I can write this as x dot plus k by m, x is equal to 0. And now you see, we have again found out our equation of motion. And all we need to know is we wanted to know the kinetic energy and potential energy of this spring system. Okay. And once we know that, we can apply this formulation. We can try to use this equation of motion that Lagrange has suggested. And from there, we can again find the same equation of motion of a spring. And from here, then we can say, oh, this is omega square. So that is a frequency of the oscillation, and all those further things can be done. Okay. So right now we are taking simple things into consideration. You have just a spring or a simple mass that is free falling, but you can imagine when things are very complicated, or even in the example of Earth, Mars, and the Sun, where you have 3 objects, their all motion of the 3 objects is connected. Mind you, there is gravitational force, so all the forces are being exerted on each other. So the motion is very complicated. And again, for this complicated motion, what will we do? It's very difficult to actually now picturize 3 objects moving in space and interacting at the same time with each other. So in those scenarios, the Lagrange's formulation will actually help us a lot, okay, because it will make our life easier.